this first question, we're told a student investigates what happens when light travels from air to glass. Figure 1 shows the apparatus used in the investigation. So we have a ray box which is providing light, and as it enters the glass block, the light bends towards the normal, and as it exits the glass box, the light bends away from the normal. So bending of light is refraction. In this question, we're given a graph and we're asked to use the graph to calculate a value for angle y divided by angle x. So I've drawn a line on the graph, as you can see, and angle y ends up being 14 and angle x ends up being 20. So 14 divided by 20 gives me 0.7. Then for the next question, it says the student concludes that the angle y is directly proportional to angle x. Explain what the student must do to test this conclusion in more detail. Well, at the moment, the student's only done two angles up to 20 degrees, so the student should repeat the experiment with more values of x which are greater than 20 degrees to get more results. In this question, we're told that the speed of light is 3.0 times 10 to the power of 8 meters per second. The wavelength of yellow light is 5.8 times 10 to the minus 7 meters. Calculate the frequency of light, and we're given the equation to use. So if we substitute our numbers in, we would put the speed of light, which is 3 times 10 to the power of 8, divided by the wavelength, which is 5.8 times 10 to the minus 7. And if we calculate that out, we get an answer of 5.2 times 10 to the power of 14, and the units for frequency is hertz. In this question, figure 3 shows a Geiger-Müller tube, which is used for measuring radioactivity. And the question is, describe how a teacher could use the Geiger-Müller tube to compare the count rates of two different radioactive rocks. So first of all, the teacher would take a background count rate so that we know what the background radiation is, and that would be subtracted from our end results. Then they would put each rock one at a time in front of the tube, and for a known period of time, they would measure the count rate. Then you would swap the rock for the other rock and do exactly the same. For the same known period of time, you would measure the count rate on the Geiger-Müller tube. And you could repeat this several times for each rock to get the average count rate. And from your average count rate, you would then deduct the background rate to find the count rate for each rock. In this question, we're told that the hospital uses a radioactive isotope with a half-life of 6 hours. A technician measured a count rate of 80 counts per minute CPM from this isotope. And so we've got a graph with count rate and time in hours. We had to complete the graph on figure 4 as accurately as possible to show the count rate from the isotope will change from the time of the first measurement. And the first measurement was already drawn on for us. So the key was the half-life being 6 hours. So if we started off at 80, that means after 6 hours, the count rate would have dropped to half, which would have been 40. So that would be at 6 hours. And then after another 6 hours, it would half again. So that would go to 20, and that would be at 12 hours. And then after another half-life, that would half again. So that would go to 10, and that would be at 18 hours. So we plotted our points and we drew our curve of best fit. Then for the next part of the question, part C, it says one radioactive source used in hospitals is technetium. Technetium is produced by the radioactive decay of molybdenum, and complete the following nuclear equation. So we've got our symbols here, and we can see that we have 99, and our decay is beta decay, so it has 0 mass. So the mass of our product, technetium, is going to be the same. It's going to be 99. However, if we look at the atomic number, we've got 42. And because beta decay is an electron, it's actually -1 that we have at the bottom there. So the number that we would need to have at the bottom would be 43, because 43 minus 1 is 42. In question 3, we're shown figure 5, which is a tuning fork. And it says when the prongs of the tuning fork are struck, the prongs vibrate in the direction shown by the arrow in figure 5, which is there. It says describe how the vibrating tuning fork causes a sound wave to travel through the air, and we can add to the diagram if it helps us with our answer. So basically what's going to happen is when we strike the tuning fork, it's going to make the air particles vibrate. And because they're vibrating in the same direction as in the way in which the wave is traveling, that's going to produce a sound wave. For the next part of the question, we're told the following description describes waves from different parts of the electromagnetic spectrum. Complete each description by adding the name of the wave. Use the name of each wave only once. Each description refers to a different part of the electromagnetic spectrum. So that's important, that we're only using each wave once. So first of all, we have the part of the wave that's used in cooking. It's used in short-range communication, and the typical wavelength is 900 nanometers. So all of these questions are just reflecting on whether you've learnt the electromagnetic spectrum and what the different parts are used for. So the first part should be infrared, or IR waves. Okay, now for description 2, type of wave that's used in cooking, but it's also used in communication, and the typical wavelength is 150 millimeters. So that there would be microwaves. Then description 3 is also used in communication, but this time it's produced by oscillations in electrical circuits, and the typical wavelength is 150 meters, so that's a very large wavelength there. So that would be radio waves. And then description 4, used in medical scanning, and it's emitted by the nucleus of an atom, so that gives us a hint there. And the typical wavelength is 2.0 times 10 to the -3 nanometer, so extremely small wavelength, which means lots of energy. So that's going to be our gamma rays. In this question, part C, when white light crosses the boundary between air and glass, it can be split up into the colours of the spectrum. Explain in terms of speed why the light behaves like this. So first of all, we need to appreciate that the different colours that make up white light have different wavelengths. Now, because they have different wavelengths, that means they're travelling at different speeds. And because they're travelling at different speeds, when they hit the glass prism, they're going to be refracted by different amounts. In question 4, we're told that the symbol g can be used to refer to acceleration due to gravity. Acceleration due to gravity has the units of meters per second squared. Gravity can also have another unit. Which of these is also a unit for gravity? So if we think of another equation where we have gravity, we can have weight, which is a force, equals mass times gravity. And if we rearrange this equation, gravity is weight, again, which is a force, divided by mass, and the units of weight would be newtons, and the unit of mass would be kilograms. So the unit of gravity here would be newtons per kilogram, and so our answer would be D. Then if we look at part B, we're told that two students try to determine a value for gravity, a value for G, the acceleration due to gravity. They measure the time t for a small steel ball to fall through a height from rest. They measure time to be 0.74 seconds using a stopwatch, and they measure the height to be 2.5 meters using a meter ruler. And we've got to calculate gravity from the student's measurement using this equation. So if we substitute our numbers in, 2h would be 2 times 2.5 meters divided by time squared, which would be 0.74 squared. And if we calculate that out, we get an answer of 9.1 meters per second squared, and that's to one decimal place. Now for this next part of the question, we're told that they record the time t for two more drops from the same height, and then we have our three values of time there. Calculate the average time t to an appropriate number of significant figures. Now, because our results are recorded to two significant figures, our answer should not be any more than two significant figures. So we would do 0.74 plus 0.69 plus 0.81, and because we've got three results, that would be divided by 3. And if we calculate that out, we get an answer of 0.75, which is the maximum number of significant figures you can give. We could give our answer to one significant figure, that would be correct too. Then for part C, it says explain one way the student could improve the procedure to obtain more accurate results for G. So the inaccuracy here comes from the reaction rate of the person timing. So what they could do is they could use something like light gates in a data logger to record the time taken to eliminate any reaction time errors that there are due to human error. Now, for the next part of the question, we're told a car travelling at 15 metres per second comes to rest in a distance of 14 metres when the brakes are applied. Calculate the deceleration of the car. Use an equation selected from the list of equations at the end of the paper. So remember, you do have those list of equations at the end. So the equation that we would use here is acceleration is v squared minus u squared divided by 2 times the distance. And if we substitute our numbers in, we get minus 15 squared, and that's because we've got our final. So here, our final velocity, because it's coming to rest, is going to be 0. So 0 minus the initial velocity, which is 15 squared, gives us minus 15 squared, divided by 2 times the distance, so 2 times 14. And if we calculate that out, that gives us an answer of deceleration at 8 meters per second squared. So the deceleration is 8 meters per second squared. Now, if we were writing it as acceleration, then we would put minus 8 meters per second squared. But because we're giving it as a deceleration, it's 8 meters per second squared. In question 5, we are asked which of these is a non-renewable source of energy. So we've got geothermal, natural gas, tidal and solar power. So the non-renewable, the fossil fuel would be the natural gas. Then for part B, it says explain why renewable sources provide an increasing fraction of the electricity supply for many countries. So this would be because Non-renewable resources are finite, they're going to run out. So we need to look at ways of decreasing our use of non-renewable energy. Then for part C, electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1,300 joules of kinetic energy. So therefore, the kinetic energy is coming from the gravitational potential energy. So the gravitational potential energy change is mass times gravity times height. And if we use this to substitute our numbers in, so all the kinetic energy came from the gravitational potential energy, so that would be 1,300 joules is going to equal the mass, which is 7.0 kilograms, times gravity, which is 10, times our height. And if we rearrange this, we would have 1,300 divided by 10 times 7, which is 70, which gives us the height. And if we calculate that out, we get a height of 19 meters. In this question, we're told as water enters the turbine at the bottom of the dam, the kinetic energy of 8 kilograms of the water moving is 1,100 joules. And we've got to calculate the speed of the moving water as it enters the turbine. So the equation that we're going to use is kinetic energy is a half mass times velocity squared. And if we substitute our numbers in, kinetic energy is 1,100 joules, and that equals 0.5 times the mass, which was 8 kilograms, times velocity squared. So 1,100 equals 4 times velocity squared, which means velocity squared is 1,100 divided by 4. So velocity squared is 275. And if we calculate that out, then we would do the square root of 275. So if we did the square root of 275, our answer here would be 17. Now in this final part to question 5, it says moving air can be used to generate electricity in a wind turbine. Figure 6 is a graph of kinetic energy against the wind speed of a mass of moving air. So we've got our figure 6, and it says just before the air reaches a wind turbine, it has a wind speed of 15 meters per second. When the air goes through the turbine, it has a wind speed of 13 meters per second. As the air moves through the turbine, some of its kinetic energy is transferred to the turbine. Use the graph to determine the percentage of the kinetic energy transferred to the turbine from the air. So first of all, we needed to calculate the amount of kinetic energy at 15 meters per second and 13 meters per second. So we can draw on our graph to figure that out. And on my graph, I got it as at 15 meters per second, it was 5.2 kilojoules, and at 13 meters per second, it was 3.9 kilojoules when it had gone through the turbine. So the difference between the two is 1.3 kilojoules. So that's how much, according to those figures, was transferred to the turbine. So that was out of the initial 5.2 kilojoules that was supplied. So 1.3 out of the 5.2 was supplied to the turbine, and to turn that into a percentage, we would then multiply by 100. And if we work that out, that calculates to 25%. Now, the answer would be a range here because it depends on how you draw your graph. So the answer here would be anything in between 18% to 32% for your final answer. Now, for the final question, question 6, part A says a student investigates the relationship between force and acceleration from a trolley on a runway. Figure 7 shows some of the apparatus the student uses, and we're given our diagram there, figure 7. Part 1 says describe how the student could increase the acceleration force to the trolley. So if we want to increase the acceleration, what we would need to do is we would need to add mass to the weight hanger at the end, and that would cause our trolley to accelerate. Then part 2 says describe how the mass of the moving system can be kept constant. So what we would do here is we would remove mass from the actual trolley so it equals the mass that we've added to the hanger to get it to move at a constant speed. In this part of the question, we're asked to explain how the student could improve the procedure to compensate for the effects of frictional forces acting on the trolley. So what the student would do, they would just raise one end of the runway or the ramp so the trolley just begins to move, and that compensates for the frictional forces. In this question, we're shown figure 8, which shows two objects, Q and R. So we've got Q and we've got R. Before and after they collide. So before the collision, R is stationary. There's no force arrow on it. It's not moving. So it has zero velocity. So the only momentum is due to Q. But after the collision, Q and R are both moving. Now, in terms of what we're asked to do, it says the arrow shows the direction of movement of the objects. The arrows are not to scale. Explain how momentum is conserved in the collision. Use Newton's third law and Newton's second law in your answer. Newton's second law can be written as force is change in momentum divided by time taken. So if we look at this, momentum is mass times velocity. So that's how to start with. We know that R has no momentum because the velocity is zero. So Newton's second law means that there's an action and an opposite reaction force. So the force of Q on R would be in the opposite direction to the force of R on Q. So the change in momentum of Q divided by the time taken in the collision is equal to the minus the change in momentum of R divided by time taken. Now, the key thing here is that the time taken is going to be the same for both of them because they're both involved in the collision. The time taken is the same. And because the time taken is the same, that then means that the change in momentum of Q equals minus the change in momentum of R. And what this means is overall, there is no change in momentum. The momentum before is equal but opposite to the momentum after. However, Q is going to transfer some of its momentum in the collision to R, which is why Q then decelerates after the collision and R accelerates after the collision.